A very good morning, students. In this video, we will learn about the continuous memory allocation. This is a topic in operating systems under memory management. Continuous memory allocation was used in traditional operating systems wherein memory was treated as a big block which was available, and as the processes would keep coming, the memory was divided into several parts based on the requirement of the process. In this method, the process is not subdivided into any pages or segments. The whole process needs to be allocated continuous one block, and therefore it is known as the continuous memory allocation because the pages are not divided, the memory is not pre-divided. As and when the processes keep coming in, the slots are created, and when the processes move out, then the continuous two slots which are present, they may be combined for allocation. So let us look at this method in detail. In continuous memory allocation, the operating system is going to reside in one part of the memory which is known as the low memory, and then we have the high memory where the user processes are allocated. Now in this user process memory allocation, there is a base register also known as the relocation register, and there is a limit register. Each PCB that is allocated to a process in the main memory has a base register pointing the location in the memory where the PCB is going to start. And then there is a total size of that block which is allocated to the PCB, and that is stored in the limit register, and the last address of that block is calculated by adding the base register with the limit register to get the last address of the PCB. So this arrangement is shown in this diagram. So the CPU, it has a logical address. The logical address should be less than the limit register's value, that is the total memory which is allocated to the PCB. That should be more than the logical addresses that are contained in the instruction. Then if it is so, if this is yes, that means that the base register or the relocation register's contents can be added to the logical address to generate the actual physical address in the memory. And this is how the logical addresses which are attached to the instructions are converted into a physical address. I will be taking up another video discussing about the logical and the physical addresses in detail. So moving ahead, in the continuous memory allocation, initially there is a operating system, there is a process 5, process 8 and process 2 in the memory. Process 8 vacates the memory after completion. Now this portion becomes free. When this portion becomes free, it can be allocated to other processes by further dividing them into the sizes which are required by those processes, and there is still free memory. That means more processes can be executed. Now that part of the memory which is not allocated to any process is known as the hole, and this creation of holes leads to two types of problems. Okay, I'll be talking about the problems. First, let us discuss the two methods of memory allocation. So when the processes are allocated the memory, when the process leaves the memory, a hole is created which may be allotted to other processes. Now, in order to fulfill the requirements of the process, there are three methods which are followed. As the memory becomes divided into several different sized blocks, which are randomly created, merged, anything can be done with those blocks. Now the allocation happens using three methods: first fit, best fit and worst fit. In first fit, whichever block first meets the request, that is allocated. In best fit, we sort the different blocks on the basis of size, and whichever minimum size block meets our requirement, we will allocate that. And in the worst fit, the largest block is allocated to the new incoming process. I will be taking up a numerical of all the three methods at the end of this video. Now, so let us look at the numerical. In this numerical, there are four processes which are entering the memory. The first process P1 has a size of 100 bytes, second process has a size of 148, third process has a size of 50 bytes, and the fourth process has a size of 200 bytes. Now, there is a MMU unit, and this is the memory that we have, which is already been divided into several blocks because of the previous allocations. Now the block 0 to 100. This block, the first entry is made, 0 is the base, the last address of the block is 100, so 100 minus 0 is 100, which is the limit or size of the block. Then the next block starts at 100, ends at 200, so the limit is 200 minus 100, 100. So the block base is at 100 and the limit is also 100. Then the next block 200 minus 350, so it is 200 starting and 150 is the limit, that is 350 minus 200. Similarly, 350 minus 500 is 150, then 900 minus 500 is 400, and 1200 minus 900 is 300. And these are the bases where the blocks are beginning, and these are the limits of these blocks. Now we have to allocate the memory to each of the process using all the three methods. The first method is first fit method. In the first fit method, whatever process comes in, we just find the first limit which is equal or greater than the size of this block that is required, and that is allocated. So as we can see, the first block is already occupied, so we will not do anything with this block. This second block has a limit of 100 and our requirement is 100 bytes. So we allocate P1 to this block. Then next requirement is 148 bytes and the next block of 150 is free, so we allocate here. Then we require 50 bytes and the next vacant block in the memory block page is this 150 block, so we allocate this and P3 occupies this block. Then we read the memory of 200 bytes and the next block which is available is 400 size, and this meets our requirement, so we will put P4 here. As we can see, this 300 size block was also available, but since this 400 was available first, so we have made an allocation here. So in first fit, whichever block first meets our requirements, that block is allocated. Now here we can see that in this P2 processes case, the requirement is 148 bytes and the size of the block is 150. Now making a new entry for the leftover 2 bytes is not suggested. Why? Because 2 bytes cannot be allocated to any process. So this kind of a hole in the memory is known as the internal fragmentation problem, which exists in the continuous memory allocation method. Then we have the second type of allocation, which is the best fit method. In the best fit method, we sort all the blocks in ascending order, and whichever block first meets our requirement, that is selected. So we have a requirement of 100 bytes, so we can start from here 100, 150, 150, 400, 300. Minimum size block is 100 and our requirement is also 100, so allocation is made here. Then we need 148 and there is a 150 block over here, which is the smallest in all and it meets our requirement, so we will allocate this. Then we need a memory of size 50 bytes. We again sort the remaining 3 blocks. Now the smallest available block is 150. A less than that size is not available, so we will make an allocation here. Then we need 200 bytes and we sort the remaining 2 blocks, and when we sort the remaining 2 blocks, 400 and 300, 300 is minimum, so we will allocate here. So best fit will always select the nearest match that is required by the process. Then we have the worst fit method. In the worst fit method, we will allocate the largest block to every process that comes in. So we do the reverse sorting and then make the allocation. So this 100 bytes is allocated the largest block of 400, then 148 comes in, and the next largest block is this 300, so we allocate that. Then the next is 50 bytes. The largest block that is available is this 150 block, so P3 is allocated here. Now when we try to allocate 200 bytes to process P4, there is no free memory, no free continuous memory. There is 100 bytes here and 150 bytes here, total 250 bytes are available, but it is not continuous. This kind of a problem is known as an external fragmentation, where the total memory that is available is equal to the size of the process, but it is scattered in the memory and therefore it cannot be allocated. So, to deal with this external fragmentation, the method is compaction. Compaction says from time to time this table is updated and all the processes are moved to one end and the free memory is made available for the incoming processes. So as we can see here in the worst fit method, this block and this block is free. So what we will do is we will add the total memory. So it is 150 plus 150 plus 100. So this is total 400. Out of this, 150 is allocated to process P3. So P3 will be shifted in the upper part and P3 is allocated there 100 to 150. Then after 150 is allocated, 250 memory is remaining. That is created as a new block here of size 250 and that is allocated to the process P4. And the remaining blocks are kept as it is. So this way compaction is performed for combining different blocks in the memory. If you like my video, please subscribe to my channel and share it with your friends, and do write comments in the comments section about how you like the video. Thank you very much for watching the video. Have a good day.